Okay, this is the final exam for Physics Lab 2 from spring 2011. This first one was to draw a ray, a practical, where you're supposed to draw a ray using the parallax method through a glass slab and then measure and label the incident and refracted angles, or something like this. So this is your glass slab. You're supposed to put 2 pins here, and then use a ruler to draw the incident ray. And then this is the incident angle. I'll call this theta 1. Alright? And then you're going to use 2 pins to draw the refracted ray. It's going to look something like that, right? Using the parallax method. Right? Then all you had to really do is to measure this inside angle, theta 2, and we know that this N1 is equal to 1, and we want to know what is N2 equal to. And so we say N1 sine theta 1, once we have those angles, is equal to N2 sine theta 2, and then you solve for N2. So N2 is N1 sine theta 1 over sine theta 2. Alright, so I was looking for your pin marks here and here, here and here, and then once you draw this line, you connect the 2 lines, alright, so that shows the path of the light ray. The index of refraction should have been something like 1.5. Alright, set up a 2-lens system with the big lens closest to the object, that is first, and a smaller lens after it, and calculate the focal lengths of both lenses. Also determine the total magnification of the lenses. Draw a figure of the 2 lenses here showing the pertinent distances and calculations. The figure should look similar to that. In problem 6, where there are the object and image distances labeled. Alright, so have your big lens here. Your object, I was looking for this figure, is right here. This distance is going to be P1, that's my first object distance. Then the image from this lens is going to be over here. So this distance is Q1. Then we're going to put in the second lens. We're going to put the second lens, say right here, and then this distance becomes P2. The image from the first lens becomes the object for the second lens. Then you're going to find the location for the image from the second lens. Excuse me. It's going to be about right here. So this distance is going to be Q2. So now you've measured the distances P1, Q1, P2, and Q2. You can use those to find the focal length for the big lens. The focal length for the big lens is 1 over P1 plus 1 over Q1. That's for F big. F small is equal to 1 over P2 plus 1 over Q2. This should have been approximately 20 centimeters. This should have been approximately 15 centimeters, give or take a couple centimeters. All the lenses are just a little bit different. So some of them are very close to that and others are not so close. Then you also want to find the magnification. You first have to find the magnification of the first lens. That is M1 is negative P over Q, or excuse me, negative Q over P. That's Q1 over P1. M2 is negative Q2 over P2. So you find values for both of these, and then the total magnification is equal to M1 times M2. And then that's what goes here. Right, your numbers are going to be different based on how you set up the numbers for P and Q, P1, Q2, Q1, P2, and Q2. They'll be different based on how you set up the lenses. Alright, the following table gives the current measured when a power supply is connected to a series of resistors. Plot the data and graphically determine the voltage provided by the power supply. Alright, so I have R and I. I know that V is equal to I times R. And so if I have R and I want to find V, I can rewrite this as I is equal to V times 1 over R. So I'm going to plot I on my y-axis, 1 over R on my x-axis. I, 1 over R. This is going to be a straight line. You find the slope of that line. The slope is equal to V. I want to sketch the circuit for a multiplier resistor used to increase the range of the voltmeter. This is my voltmeter. This is my multiplier resistor. I put it in series with the voltmeter. Right, describe how it increases the voltmeter. The multiplier resistor splits the total voltage with the voltmeter. You could have said that in so many words. You could have also said it in this figure, like say for example, if I get 90 volts here and 10 volts here, my voltmeter is reading full swing. It's reading the max that it can read, but really across these 2 points I've got 100 volts. So that is a 10-fold multiplication. Describe how a galvanometer works. You've got a coil of copper wire. It has a current flowing through it. It has a needle attached to it, a dial, if you will. When current flows through it, this current flows through this coil. This coil sits inside a magnet, inside a permanent magnet, and the magnetic field on the coil of wire interacts with the magnetic field, causing a force. So when you get this current that flows through this coil of copper wire, there is a force exerted by the magnetic field. So you get a force. What is the total magnification of the object, which is located 20 centimeters to the left of the lens for the system of convex lenses? This is not a compound microscope, so you have to actually work through the lens equation. So P1 is 20. Let's go ahead and solve. This is F1, so we need to solve for Q1. Q1 is equal to 1 over F1 minus 1 over P1. The inverse of that is 1 over 10 minus 1 over 20. The inverse of that, and I get 20 centimeters. Let's go ahead and solve for the magnification. So M1 is minus Q1 over P1. So that's going to be negative 20 over 20, which is negative 1. So that means it's going to be the same size as the object, but inverted since it's negative. Alright, it's 20 centimeters. That's about right here. So if I were to sketch that in, it'll look right there. Now, this distance becomes P2. So let's solve for Q2. 1 over F2 minus 1 over P2 to the negative 1. It's 1 over 20 minus 1 over 40. Inverse of that, I get 40 centimeters. Alright, this distance is 40, my focal length is 20, 1 over 20 minus 1 over 40, that's equal to 40, the inverse of that. Solve for M2, negative Q over P, that's negative 40 over 40, that's equal to negative 1. All right, that means that the object is going to be inverted again, but the same size. So then it's going to be right side up, but still the same size as the image that was right here, which was the same size as the original object. So my total magnification is equal to m1, m2. Negative 1 times negative 1, just positive 1. Let's see, what are they asked for? Total magnification, that's all I wanted to see. Alright. Sketch two light rays originating from this object whose position is labeled with an X. Locate the position of the image, measure and label the image and object distances. So this wasn't a practical, you're just supposed to draw two rays. There's one ray. Law of reflection says those angles are equal. Do another ray, shallower. You would use a ruler, so this would look a lot neater. I trace this ray back. I trace this ray back. So this is the location of my image. Then you use your ruler to measure Q, use your ruler to measure P, and that's all. Measure and label the image and object distances. How is the tangent galvanometer used to measure the Earth's magnetic field? Sketch the vectors representing the Earth's magnetic field and the magnetic field created by the tangent galvanometer. Alright, tangent galvanometer, the coil of copper wire. It creates a magnetic field. If my current is in this direction, that magnetic field is out of the page, like that. So you orient it so that the magnetic field you create is perpendicular to the Earth's magnetic field. And we can sketch that here. This is the magnetic field you create. This is the magnetic field of the Earth. And by measuring the deviation caused by this man-made magnetic field, how much does the compass deviate, you can calculate BE. So measure deviation to calculate BE in so many words. Given this table is the data for the number of turns of wire, current and angle of deflection for a tangent galvanometer. There's the radius. Graph it, calculate the Earth's magnetic field. Okay, I know that Ni, this is on your equation sheet, is equal to 2RBE over mu naught times the tangent of theta. So I want to plot on my y-axis Ni, my x-axis tan of theta. Right, it's going to be a straight line. You want to find the slope. I don't know what the slope is right off, but you're going to set the slope equal to 2R BE over mu naught. Remembering that mu naught is 4 pi times 10 to the minus 7, that's in Tesla meters over amps. R equals 0.4 meters, that's given in the problem, and then you solve for BE. It should have been in the order of 20 or so microtesla. But you want to find the slope of that graph. Okay, following the schematic for 6 terminals on a double pole double throw switch. If the switch is in the down position, so the path that the current takes through the circuit. So that means that the switch is going to be in this direction. So if my current comes here, it goes there. There are 2 wires that travel like that. So that means my current flows through that wire, through there, back there, and then back to the power supply. So my current flows right to left through that resistor. What is the purpose of a double pole double throw switch? To change the direction of the current. It's actually a pretty ubiquitous type of switch. I said in DC motors, other types of motors. Change the direction of the current. Sketch the path of the incident light ray through this glass prism. This is my normal line. It's going to bend towards the normal here. Normal line, and then it's going to bend away from the normal there. Calculate the magnification of the compound microscope in this figure. Alright, the compound microscope, M is equal to negative 25 x prime over FO FE. This is my objective, this is my eyepiece, this is x prime. Excuse me, that's not x prime. Actually, x prime is the distance between the two focal points. So this is x prime. So first you need to calculate what is x prime. So x prime equals 60 minus 25 minus 15. Which is 60 minus 40, so x prime is equal to 20 centimeters. So it's going to be minus 25 times 20 centimeters. And this is all in centimeters, by the way. This minus 25 comes from the near point of the human eye, so it's also measured in centimeters. Times 15 over 25. Or times 15 times 25. See, the 25's divide out, so I get 20 over 15. What's that? 4 over 3. So it's 1.33. Negative 1.33. That's the final answer. What causes chromatic aberration? Draw a figure and explain. Chromatic aberration occurs only in lenses. If I have blue light that comes in, it focuses at a particular point. If I have red light, or of a different wavelength, that comes in along the same path, it's going to focus at a slightly different place. It does this. This, by the way, is our chromatic aberration, this delta F. It does this because N is dependent on wavelength. N is dependent on the wavelength. As the wavelength changes, the index of refraction changes. How are stars classified as different spectral types? By emission and absorption lines. Primarily by emission. Whoop. Excuse me. By emission lines in their spectra. Alright, is the following emission from a hydrogen or helium? Hydrogen only has a couple of lines. Helium, I see a number of lines here. So that's helium. Helium actually has more than that, but that's all that we could see in our spectrum. And that's all.